This lesson is for section 7.2. We're going to be looking at trig functions of angles. So we have three different objectives for the day. Our first objective is to use the unit circle to calculate trig functions of an angle. We talk about the unit circle here, and we're going to actually do this from memory. We're going to complete a chart for the unit circle from memory, and we're also going to use a calculator to evaluate trig functions. So we use both a chart of the unit circle. This would be when we evaluate trig functions without a calculator. And we'll also teach you how to use your calculator as well. Did I spell that right? Calculator. There we go. So that you can evaluate trig functions also. Okay, now let's talk about some vocab. Okay, now recall that the study of trigonometry really is just the study of the angles of a triangle. Okay, now when we look at angles, it's really easy to put an angle anywhere we want it. Okay, this is not something in standard position. When we look at trigonometry, we want to think of all of our angles in standard position. So this is what standard position looks like. Notice that you have one of your rays located on the positive x-axis. Okay, so this would be an angle written in, or drawn in standard position. Now we have two sides. We have an initial side. This is the ray that's lying on the x-axis, and the terminal side. Okay. Now, when you go clockwise, this is actually a negative angle measure. Okay, so if you were to consider this, this would be a negative angle measure here, and when we go counterclockwise, this is a positive measure. So this angle here could be written as, let's say it's 40 degrees. So this would be positive 40 degrees, or if we take 360 and subtract here, that would be negative 320 degrees. Okay, so there's two measurements for the exact same angle. So positive 40 when we go counterclockwise, and when we go clockwise, that's a negative direction. Okay, now these would be coterminal angles. Okay, these are two angles that are in standard position that have the same terminal side. So here's my terminal side. So 40 and negative 320 are coterminal angles. Okay, now next up we're going to be talking about trig functions. Now the input for a trig function in this chapter will be angle measures, and our outputs will be real numbers. So we're going to be studying functions that have specific names, kind of like how log is the name of a function. Here we're going to be dealing with names like sine, cosine, tangent. And we're going to talk about each one and define them in regards to the unit circle. Okay, so now let's talk about some trig functions. Now, the cosine and sine, these are words that you probably are familiar with, but not in reference to a unit circle. You probably have seen sine and cosine when you were looking at right triangle trig and solving right triangles, which is going to have some similar applications here as well, but what we look at is a unit circle. So we take a unit circle as just a circle with radius 1. Okay, so it has a radius of 1. Now, the functions cosine and sine produce the x and y coordinates on a unit circle for any given angle. So the cosine of theta, notice our input, like we talked about just a second ago, is an angle measure, and our output, x here, is a real number that lies on the unit circle. Okay? So the cosine of theta is your x coordinate. The sine of theta is your y coordinate. So here, the point x, y can also be written as the cosine of theta, comma sine of theta. So p, this coordinate here, is cosine theta, that's your x value, comma sine theta. So it just produces an x, y output. Okay, now we also have other definitions for trig functions. Now we just talked about cosine and sine, so this is how they're actually written out. And abbreviated like so, cosine, sine. But we also have the tangent function, which is just the ratio of the sine over cosine. And we have these things called reciprocal functions. So the secant, cosecant, and cotangent, these are called reciprocal functions. So as we defined earlier, the cosine of theta is equal to x. So we have an input that is an angle measure and an output that is a real number. Okay. Now, the tangent of theta is simply the ratio of sine of theta over cosine theta, which is why we get y over x, and x cannot equal 0, otherwise it's undefined. Now, the secant of theta is simply the reciprocal of the cosine function. So we have, if we take the reciprocal of cosine, we end up with 1 over cosine theta, which is equal to the secant of theta. So 1 over cosine theta is equal to 1 over x. Okay. we take the reciprocal of sine. We have 1 over sine theta, which is equal to 1 over y, which we define to be the cosecant of theta. And finally, if we take the reciprocal of our tangent function, so looking at this fraction here, this ratio, if I take the reciprocal, I end up with cosine theta over sine theta, which is x over y, which we define to be the cotangent of theta. Okay, so you're going to see me write it two different ways. Sometimes you just see cotangent theta and then cotangent of theta in parentheses. They mean the same thing though, okay? So basically, all you have to really remember are these two main ones. The cosine of theta is equal to x, the sine of theta is equal to y. If you get that mixed up, then you're going to be in worlds of trouble. But if you can get those, then the rest of them kind of fall into place. The tangent, just remember y over x, it's sine over cosine. So sine actually comes before cosine there. And then after that, it's just reciprocals. So you're taking, the opposite, I'm sorry, not the opposite, the reciprocal of each of those functions. For me, it was really hard to remember that sine and cosecant went together. I always wanted to do cosine and cosecant, so the cos don't actually coexist. So cosine and secant are paired together, sine and cosecant, and then tangent and cotangent. That's pretty obvious, cotangent, tangent. All right, so let's take a look now at the unit circle and derive a little bit of the values, the coordinates on this unit circle. Okay, so we've got a blank circle here, and I know that in the unit circle, my radius is 1. So if I go through here and I have a radius of 1, that means that this coordinate here is the coordinate 1, 0. Okay. And that's just because I know that this segment here is 1. I also know this segment here is 1, 1, 1, and so on. So I can actually do all of these coordinates here already. This is 0, 1, this is negative 1, 0, and 0, negative 1. Okay, so that doesn't really take much effort for us to do that. Now, when we list, this is only going to be part of the unit circle. We have a lot more values to remember after this, but we're going to do just our very basic values on this unit circle. Now, let's talk about the angle measures, both in radians and degrees. Now here, at the point 1, 0, this measure for the angle is 0 degrees, okay, or 0 radians. However, if I go one revolution all the way around the circle, this is also 360 degrees, or 2 pi radians. Okay? Now, if I go to the point 0, 1, now this coordinate here is at an angle of 90 degrees. That's pretty obvious for us that have taken geometry, so this is 90 degrees. We also can call that pi over 2 radians. Now, you can always get these values by taking pi over 180 and multiplying it and converting, but it's also just better for you to memorize these. But it's easy too just to think of this, okay, if I went all the way around and that's 2 pi, then over here, that's got to be just pi. And this semicircle here, cut in half, would mean that that's half pi, okay? Now, I already went and filled in the pi radians here. This is also 180 degrees, okay? And if I go another 3/4 of this circle, I'm at 270 degrees. And if I add half a pi, right, this is 1/2 pi to pi, I get 3/2 pi. Okay, so there's my measures. Now, if I were to go in a negative direction, I would define this coordinate here to also be negative pi over 2 radians. Okay. I could also say that that's negative 90 degrees as well. So just be careful about being able to go both counterclockwise and clockwise. All right? So let's do some values where we're calculating using our trig functions. So we're going to use our unit circle, and we can just look at and reference this picture here to find these specific values. So let's take a look at the cosine of pi over 2. So the cosine of pi over 2, remember, this is the angle input. So our pi over 2 would be at this measure here. So this is pi over 2 radians. So I'm looking at this coordinate, 0, 1. Whoops, move that around. So I'm looking at the coordinate 0, 1, and I want to take the x value. Remember, cosine of any angle measure gives me the x. So I have cosine of pi over 2 is 0. It's the x value for this coordinate. Now the tangent of pi over 2, remember this is sine over cosine. Okay, so I'm going to look at pi over 2 again. So I'm still at this angle measure here, 0, 1, and I'm going to take the y value, 1, over 0. This is undefined. So in this case, the tangent of pi over 2 is undefined. Okay, next up we have C here, the secant of negative 270 degrees. Now, our input here is in degrees. That's okay. It doesn't change how we solve this problem. But we do have a negative value here. So that means that our angle is actually going to go in a clockwise direction. So we start here at 0, and we go negative 270 degrees. So we go clockwise 270 degrees, and we actually end back up at the coordinate 0, 1. So it's actually really equivalent to 90 degrees. These are coterminal angles, negative 270 and 90. So I'm going to look at the secant of this value. So remember, secant is just 1 over cosine. Okay, it's the reciprocal function. So this is really 1 over the x value. So I take a look at this and I see 1 over 0, which is undefined. So the secant of negative 270 degrees is actually undefined. Now in D, again, I have a negative value. This time it's in radians. So I start at 0 degrees here, and I'm going to go backwards, clockwise, and I end up at the coordinate here. If I go pi over 2, I end up at 0, negative 1. So the sign here, sign of negative pi over 2, is simply negative 1. Remember, it's the y coordinate. Okay, it's the y value. Now the cotangent of negative pi over 2, so I'm still at negative pi over 2, that means I'm still looking at this value. Cotangent is the reciprocal of tangent. Tangent is another one you want to definitely memorize. It's just y over x. It's the cosine, the sine over the cosine. Okay, y over x. So if I'm looking at cotangent, I'm taking the reciprocal of this, which means that this is x over y. So I'm looking at this coordinate, 0, negative 1, and I'm going to take the x value over the y value, which gives me 0 over negative 1, which means that the value here is 0. So the cotangent of negative pi over 2 is 0. Okay, last up I have f here, the cosecant of negative 7 pi over 2. Now, this is going to go in a clockwise direction, right? But this negative 7 pi over 2, we haven't quite seen something like this yet. This is actually making one full revolution all the way around the circle. Remember that we have 2 pi radians, right, going around the circle, which if I write it as a fraction, that's equivalent to 4 pi over 2. So this is actually one full revolution, right? 7 pi over 2, so negative 7 pi over 2, is equal to 1 complete revolution, and then plus another 3/2 pi around that circle. So if I went all the way around one time, that takes care of this guy here. And if I continue in that clockwise direction, negative 3 over 2 pi, I end up right here at pi over 2's coordinate, 0, 1. So these are coterminal angles, okay? So I have 0, 1 is the coordinate that I'm going to look at. So the cosecant here is going to be the reciprocal function of sine, 1 over sine. So I'm looking at the y value here, which is 1. So I end up with 1 over 1, which is 1. So the cosecant of negative 7 pi over 2 is simply 1. Okay, now in problem 2, we're going to actually break this up into 3 different types of problems here. The first thing that we're going to do is verify that in the diagram here to the right, that P is on the unit circle. Now, in order for P to be on this unit circle, remember this circle here is in the equation, x squared plus y squared equals my radius here, which happens to be 1. So in order for this point to lie on this graph here, it has to satisfy this equation. So if I want to double check this, if negative 1/2 squared plus negative root 3 over 2 squared is equal to 1, then it does satisfy this equation. So if I square here, I get 1/4 plus this term squared here is going to give me positive 3/4, which in fact is 1. So 1 equals 1, boom, it's on the graph. Okay, so we just verified that it's on the circle. Now, part B here says to find the 6 trig functions at theta. So if we take a look at theta, theta here is going in a counterclockwise direction, so this is a positive value, but it's still got the coordinate negative 1/2 negative root 3 over 2, right? So if I found my 6 trig functions here, let's take the cosine of theta. The cosine of theta is simply the x-coordinate, so that'd be negative 1/2. The sine of theta is going to be negative root 3 over 2. It's the y value. And the tangent of theta is the sine of theta over the cosine of theta, which is just going to be negative root 3 over 2 divided by negative 1/2. Now, we know that dividing by this fraction is the same as multiplying by its reciprocal, so I'm going to multiply that by negative 2 over 1. And these negatives will cancel out, leaving me with positive root 3. So the tangent of theta is simply root 3. Now, for the other functions, the reciprocal functions, I don't have much work I have to do here, because I simply take the reciprocals. So the reciprocal of cosine, which is going to end up being the secant of theta, is negative 2, right? I take the reciprocal of 1/2, negative 1/2. Now, the cosecant of theta is the reciprocal of sine. So if I flip this, I end up with negative 2 over root 3. Now, in our book, in our textbook, and I think probably in previous courses that you've taken so far, you probably rationalize the denominator. In case you haven't, I'm going to do that with you right here. Now, rationalizing the denominator means that I cannot have a radical in the denominator. So what I'm going to do is multiply by root 3 over root 3. Okay? Multiplying throughout by root 3 over root 3 doesn't really change this value, but it does allow the radical in the denominator to be dropped. Root 3 times root 3 is simply 3. In the numerator, I end up with negative 2 root 3. So this is in the form, these are equivalent to one another, but this is in a form where the denominator has been rationalized. So the cosecant of theta is negative 2 root 3 over 3. So I would like you to do that with all of your values so that you do not have any radicals in the denominator. Okay. Finally, for the cotangent of theta, we simply look at the tangent of theta. We take the reciprocal here, which is going to be 1 over the square root of 3. And if I rationalize here, I'm going to multiply by root 3 over root 3, and I end up with root 3 over 3. Okay, so here are the 6 trig functions here and their values. Okay, now the second, or the last part, this third part here, says to compare these 6 trig functions to the 6 trig functions at beta. This is just another Greek letter. So here you can see that it's a coterminal angle. If I compare that to this angle measure here, well, I'm using the exact same coordinates. So in part C, it's pretty redundant. I know that the cosine of theta, or I'm sorry, the cosine of beta, okay, the cosine of beta has to be negative 1/2. The sine of beta has to be negative root 3 over 2. The tangent of beta has to be root 3, and so on. So I don't actually have to do all this work because I know that coterminal angles actually have the same trig values. Okay, that was the whole point of this question here, is to see that our coterminal angles actually end up with the same exact trig values because you're using the exact same xy outputs. Okay, in problem 3, it says a point P is on the unit circle in quadrant 3 with a y-coordinate of negative 4/5. I'm actually going to have you guys evaluate the 6 trig functions on your own just to get some practice, but we'll set up, how to find that xy pair. All right, so let's start with drawing the unit circle here. And we know that point P has to lie in the 3rd quadrant, so it's somewhere over here. Now, the y-coordinate is negative 4/5. Now, to find your x value here, you have to remember that this must satisfy, since it's on the unit circle, the equation x squared plus y squared equals 1. So I'm just going to take that negative 4/5 here and substitute it in for y, so that I end up with the equation x squared plus negative 4/5 squared is 16/25 equals 1. Now, if I subtract that over, I get x squared equaling 9/25, right? 25 minus 16. Okay, now, I'm going to square root this, and I do end up with 2 possible solutions here. X could either equal positive or negative 3/5. Now, think about the fact that it's lying in that 3rd quadrant. This x value has to be negative, right? This has to be a negative coordinate. So, we're going to use negative 3/5 for the x value, so we're going to toss out the positive, okay? And now you guys can go ahead and evaluate your 6 trig functions using the coordinate negative 3/5, negative 4/5. So go ahead and practice that and check with the key. Okay, in problem 4 it says, what does pi over 2 is less than theta is less than pi actually mean? What this is saying is that this is an interval that's saying that theta has to lie between pi over 2 and pi radians. So if you were to draw that out on a unit circle here, this is 0 radians, we have pi over 2 radians, then pi radians, 3 pi over 2 radians, and then 2 pi radians. Okay, because it's one revolution all the way around would be 2 pi radians. So what this is saying is that if theta lies between pi over 2 and pi, that means that theta here must be within my second quadrant. So theta lies in quadrant 2. Okay? So this is notation that you're often going to see, and it just helps you to locate where theta lies. Okay, next up we're going to estimate some trig values, and we're actually going to look at a picture over here to do our estimating. So we're going to look at these values here and decide which is larger. So just to look at this picture here, we do have a unit circle because we have the equation x squared plus y squared equals 1. So this is a unit circle. Now if you look, this is actually written in radians. They're marking off for you 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians. Okay, because again, we know that half of that circle here, that semicircle, this gives me pi radians, or 3.14 radians. So that makes sense that 3 radians is right about here. Okay? And then, of course, going all the way around, we have 2 pi radians, which is going to be slightly larger than 6 radians. Okay, so just looking at the picture here, if we're going to look at the sine of 3, so the sine of 3 radians. 3 radians is about here. Now, the y-coordinate here is pretty low, right? This is a y change that's pretty low. If we look at sine of 1, well, 1 radian is up here. This y value is much larger, so the sine of 1 is larger. I would like you guys to try both B and C and check with the key just so you get an idea of what that really means when you're looking at, you know, the sine is just the y output, the cosine here would be the x output, and the tangent here is going to be y over x, the ratio of y over x. So go through and practice B and C and check with the key. Okay, next up we're going to use a calculator to evaluate the secant of theta, the cosecant of theta, and the cotangent of theta. You probably have already done sine, cosine, and tangent of theta in geometry, but now we're just going to be practicing inputting for both radians and degrees, which in geometry you probably only use degrees. So go ahead and take out your calculator, and let's get started. Okay, so whenever you don't see a degree symbol, you're going to assume that that means that it's in radians. So our first example here, we're going to do 30 radians, as opposed to over here we have negative 120 degrees. Okay, so one of the things that you want to do is make sure that you're in the correct mode in your calculator. So I'm going to hit mode here. Right now I'm in degrees, which would not be okay if I'm trying to evaluate the secant or the cosecant or the cotangent of 30 radians. So I need to change that to radians. So I'm just going to go down here, hit enter. And again, that was just in the mode. Second quit out of that. And then when you want to evaluate the secant of theta, remember secant of theta is really 1 over the cosine of theta. So you're going to notice that there are no buttons for secant or cosecant or any of that. Now, it's not the inverse of cosine, so you don't want to hit second inverse cosine. What you want to do here is just type in 1 over the cosine of, and we're going to input 30 degrees here, and we end up with 6.48. So the secant of 30 radians is equal to 6.48. Okay, there's our real value, our real output there. Now, I'm going to let you guys do the cosecant and cotangent. Remember, cosecant of theta is just 1 over the sine of theta. So again, don't hit second inverse. You don't want the inverse sign. You just want to do 1 over sine theta. And then cotangent of theta is simply 1 over the tangent of theta. Now, when we bounce back to this input here, which is in degrees, I need to go back to my mode and change that into degrees. Now when I hit 1 over the cosine of negative 120 degrees, I end up with negative 2. So the secant of negative 120 degrees is equal to negative 2. Again, please evaluate both the cosecant and the cotangent for in the radians and in the degree inputs here, just to get practice, and then go ahead and check with the key. All right, that's it. That's the end of the lesson. I'll see you guys in class tomorrow.